So let's start with one of the review problems, which is problem number 3 on the review set entitled Elastic PE and K and WE theorem. And it discusses a concrete pillar that is inside a parking garage, and it has a spring-loaded bumper. And what that simply means is if the car hits the bumper, the spring becomes compressed, and it reduces the force that's experienced by the car in any given instant and reduces the damage that is done. And it's asking us to discuss or to calculate what the constant is for that spring. Now, in order to do this, let's do a very quick look at what exactly is happening. A spring is made up of obviously atoms that are bonded together. And what happens is if an object collides with the spring, that object brings to the system kinetic energy. And when it bumps into that spring, it causes the bonds that are holding together those atoms, those bonds become deformed. They become strained or stretched or compressed. And the kinetic energy becomes stored in those compressed or deformed bonds. And so what you have is a transfer of kinetic energy into the potential energy being stored inside that spring. Now, some springs, such as those that are found in your garage, those springs are very, very thick. They are very stiff, and therefore they're the amount of energy that they can store and how much they get compressed is very strong. If you take the spring in a watch, that spring is very, very delicate. It's much smaller, and therefore springs have different properties to them. Springs have different abilities to store potential energy. Springs compress to different amounts when a certain amount of kinetic energy is pushed in on them. And what this question is asking it is, what is the elastic constant? What is the amount of compression that this particular spring, which is the one that's in the garage, is capable of doing? And so let's begin with what this is all about. So we're going to have a car, and that car is going to bring a certain amount of kinetic energy into a collision. Now, energy has to be conserved, meaning it has to always be accounted for, go somewhere when there is an exchange. And what's going to happen is this kinetic energy is going to become the potential energy that is stored inside that spring. Now, the kinetic energy is described by the equation 1/2 mv squared. So that describes the energy the object that's in motion is bringing to that collision. Now, the potential energy within a spring is described by the equation 1/2 kx squared. And so this is specific to the spring, and this is specific to the car that's going to undergo the collision. And again, one of the critical pieces here is that the total amount of kinetic energy must match the total amount of potential energy in the end that gets transferred. And so now at this point, we would take a look and say, right, so 1/2, the Corvette, has a certain mass, and that mass is found right here. It's 1475 kilograms. So 1475 kilograms. And the Corvette, just before it hit, was moving at a speed of 2.5 meters per second. So that's the velocity. So that becomes 2.5 meters per second. Whoops. Meters. Do it again. Here we go. Meters per second squared. So this is the total amount of kinetic energy that is entering the system. And it's all going to get transferred to the spring. And to know what's involved there is this. when it transfers to the spring deforms. Now, the more that it deforms, the farther that the spring is compressed, the more potential energy that spring can handle. And so what's going to happen is the K value is the elastic constant. And what this is telling us is this particular bumper, it compressed by 0.13 meters. So by compressing by this distance, the spring overall stored this much energy. Now we want to know is, so what is the elastic property of that spring if that's what it's able to do? And the answer becomes 54, 88, and the units on that would be newtons per meter. And that's going to be then the spring constant for the bumper. So let's take on a new problem. And this problem is problem number 8 from that same review set. It involves a car that undergoes an acceleration from rest, but there are two forces acting on it. One is from the engine that applies 1140 newtons of force through the traction with the road, and the other one is 950 newtons of resistance force due to friction. So it says that use the work kinetic energy theorem to determine how far the car must travel for its speed to reach 2 meters per second. Now let's get a diagram going here of what's going on. I wish I could draw. So there's a road. It should be nice and level, but it's not. And the road has a car. And what's happening is the car has a force going that way of 1140 newtons. But of course there's a frictional force that's going on, which is 950 newtons. Now, what this whole problem centers around is the idea that when I apply a force over a certain distance, work has been done. Now, what exactly does that mean? I think the best way to think about it is when you apply a force to an object, I always think of it as what I'm pumping in is I'm pumping in energy into the object. And the amount of energy that I'm pumping in is the work that is being done. So in other words, if I pump in a lot of energy into the object, I'm doing a lot of work. If I don't put too much energy in there, then not too much work gets done. Now the units that are used for work are in joules. So how do I know how much energy I was able to put in? Well, if I multiply the force that I've applied and the distance that I apply it over, I can calculate that. So that is how you define what work is. But what is the work energy theorem? The work energy theorem says that the amount of work that is done is equal to the amount of kinetic energy final minus the amount of kinetic energy initial. So what that says is the amount of energy that moves into that system the amount of energy that moves into that system, is the difference between the kinetic energy before and after. And that amount of energy is the amount of work that you've done. And so as you might start to realize, you could say, right, so the force applied times the distance is going to equal to the kinetic energy final minus the kinetic energy initial. Well, according to this problem, the car began at rest. And if it's not moving, there is no kinetic energy because there's no motion. So this will go to 0. So now you can write it as the force times the distance is equal to the final kinetic energy. Well, what is kinetic energy? It's 1/2 mv squared. And so what we see here is the force being applied by the engine over a certain distance is going to transfer to the object a certain amount of kinetic energy. And the amount of kinetic energy it gets is defined by 1/2 mv squared. So what it asks is, so how far does the car have to go to reach a speed of 2 meters per second? And so the difference between the amount of energy put out by the engine, which is 1140 newtons, minus the frictional force opposite direction, 950 newtons, multiply times the distance, which is what we're looking for, is going to equal to 1/2 the mass of the car, which is 2 times 10 to the third kilograms, times the ending velocity is going to get to, which is 2.0 meters per second squared. And when you crunch it, the distance it has to travel is 21 meters. So, one last time, what is this saying? It's saying that the amount of work done on an object is equal to the amount of kinetic energy it winds up with minus the kinetic energy it began with. Now, stated another way, the amount of work that is done, how work gets done, perhaps not a better way of saying it, is you apply a force on an object over a certain distance. We could then equate these two together and then punch it through. Let's take a look at one more problem from the same review sheet. It is problem number 9. And in this problem, you've got a 75 kilogram bobsled. It's pushed along the horizontal surface by 2 athletes. And then after it's been pushed a certain distance, it has achieved a certain speed. What's the magnitude of the net force? So as always, let's try to get a diagram here. Nice straight line, Mr. Karth. So we have a bobsled, and that bobsled is being pushed. And that bobsled is going to achieve a certain speed. And the question is, what is the net force that is applied? Now, this is once again an issue of work done. Now you could say, well, why don't we do F equals ma? And you could if you had certain information, such as, for example, some time issues, but we're not. So if we can't do F equals ma, what we can say is work is being done. work being done, meaning that I've applied a certain force and it's gone a certain distance. But there's another definition of work, which we saw in the last problem, which is the work energy theorem. And the work says that whatever amount of kinetic energy I end up with minus the amount of kinetic energy I started with, that will be equal to the work done. So once again, we can equate these two and say that FD equals KE final minus KE initial. Now, it indicates that it is pushed on the horizontal surface. And what we have is a key word, and that key word is right here, phrase. It is from rest that this begins. Therefore, there is no initial kinetic energy of the system. So what happens now is we want to know what the net force is. We know that this force is going to be applied at a distance of 4.5 meters. So we're going to be pushing this thing 4.5 meters. Now when you apply a force over a distance, what you're putting into the system is energy. And in this case, it's showing up as kinetic energy. And so if it shows up as kinetic energy, it's 1/2 mv squared. Now the mass of the bobsled is 75 kilograms, and the velocity is 6 meters per second, and we square that since kinetic energy is 1/2 mv squared. So when you crunch the numbers, you wind up with 300 newtons of force was applied to the bobsled.